Hey. So to finish the chapter, we've been talking about discrete random variables, talk about continuous random variables. So this is just important for the setup of what I'm going to talk about in 2 seconds, because you know how our book is. So, for example, company manufactures stereo systems. There's 2 different stages of this process, all right? There's packing it all together, all the components, right? So they put them all together in plastic bags. And then they put the packing and they box it all up at the second stage. Okay, so 2 different things going on. So technically 2 different random variables. Packing would be X, boxing would be Y. Okay, and it says down here, the company says that times required for the packing stage can be described by a normal model with a mean of 9 minutes and a standard deviation of 1.5 minutes. The times for the boxing stage can also be modeled as normal with a mean of 6 minutes and a standard deviation of 1 minute. So I've got a bunch of mean and standard deviations, but I don't have any probabilities like we've been having before. Okay? So for a continuous random variable, you don't have this list of discrete outcomes. Like you don't know, well, if this happens, it's 11%, or if this happens, it's 22%. So a continuous random variable can take on any value. No single value isn't going to have this probability that we can just figure out really fast. But a lot of the time in these scenarios, they're modeled by normal models, which we talked about in chapter 6. All right. Back then, think about the things we did with a normal model. We had first of all, what is a normal model? Like the bell curve, unimodal and symmetric, right? You had to find z-scores, where you found the number minus the mean divided by the standard deviation. We could, with our calculator, we could find areas under that curve, right? We could go from 2 to infinity. That would give us this number, right? The area under the curve. We didn't call it that then, but that's a probability. Okay, so the area under the curve is the probability that something's happening. Probability that's greater than 2, whatever it is in context. Probably that's less than 0.75, whatever that is in context. All right? So we can use some stuff we've already learned to figure this stuff out. Also important, all of those rules that we learned about discrete random variables, like adding variances and all that jazz, all that still applies. There's not new rules for continuous random variables. Okay, so we still have old stuff. This chapter is still intact. So when 2 independent continuous random variables have normal models, so does their sum or difference. So we can start adding and subtracting and doing things like that. When I do some questions with you today, the first part of it you'll be able to get. It won't be a problem. You'll be like, oh, yeah. Like you wouldn't probably even know the difference, that it was continuous or discrete. They wouldn't give all the probabilities, but you could still answer the question. Okay? But then if it asks for a probability, we're going to have to use a normal model. Okay? So I've got this great question on page 385 about cereal. Because who doesn't love cereal? You don't love cereal? Sad. What a sad existence. Oh my gosh. All right. Of course you do. The amount of cereal that can be poured into a small bowl varies with a mean of 1.5 ounces and a standard deviation of 0.3 ounces. A large bowl holds a mean of 2.5 ounces with a standard deviation of 0.4 ounces. You open a new box of cereal and pour 1 large and 1 small bowl. So important to note that you have 2 different variables. X is like your small bowl, and you have a mean of 1.5 and a standard deviation of 0.3. And Y is your large bowl, where the mean is 2.5 and the standard deviation is 0.4. Okay? So in part A, how much more cereal do you expect to be in the large bowl? This is not a trick question, just like the practice quiz, not a trick question at the end. How much more cereal do you expect to be in the large bowl? Expected value is talking about what? The mean. So how are we going to figure out how much more would be in the large bowl than in the small bowl? Right, so we're going to do Y minus X, right? And so we have, for the expected value, we have 2.5 minus 1.5, which is just 1 ounce. We'd expect a large bowl to have an extra ounce of cereal. Does that make sense? Right, that you could have done that without me having to teach anything about continuous random variables. All right, on part B, what's the standard deviation of this difference? So you can't add standard deviations or subtract them, but you can add variances, right? And we have the 2 standard deviations for each bowl size. So we're going to add variances and take the square root like we keep doing over and over and over again. So the standard deviation of y minus x is the square root of 0.3 squared plus 0.4 squared, which is what, 0.5? Okay, so we found A and B. You probably could have found those on your own, right? Those weren't anything tricky. You probably could have figured it out. If you really thought about it, you could have figured it out. Now on C, if the difference follows a normal model, what's the probability that the small bowl contains more cereal than the large one? Now, before we get there, remember normal model was defined by the mean and standard deviation. So we're using the mean and standard deviation of the difference, which we had on part A and B. So my mean would be 1 and my standard deviation would be 0.5. Does that notation look familiar? Mean, standard deviation. N represented the normal model. That's what model we were using. You're going to see a lot more notation like that in the next chapter. Okay? All right, so going back to what the question asks, what's the probability that the small bowl contains more cereal than the large one? We're talking about the difference y minus x, right? Y is going to keep having more until x, what happens with x? When with the small bowl? When x becomes larger than y, right, there's more in the small bowl, right? Yes. Well, if x becomes larger than y, what kind of numbers are we going to get? Negatives, right? Now, the equalizing point would be when they're both the same. That would be 0, right? Yeah, so that's like your boundary point. You're doing 0 and below, right? Now think about our normal model. We could draw a picture. Generally, drawing pictures is a good plan on the AP exam. If you draw the picture, you're generally going to get the points you're supposed to in those parts. We know the mean is 1. We know the standard deviation is 0.5, so I can do 1.5 to 2.5, 0.5, 0, negative 0.5. Right, this is a normal model for the difference. Right, and we're looking for the small bowl would have more if it was negative, right? In this context, yes. Because you're talking about the difference here. We're talking about the difference in the amounts in the bowls. So if x is bigger than y, we're just talking about the difference. Yeah, okay. So we're looking at this section of the curve, right? 0 and below, right? Now, we had to use our calculator to find these things. So pop quiz. Who remembers what buttons to push to get to a normal model? Oh, man. Because the question's asking us, what's probably the small bowl contains more cereal than the large one? So we've been using y minus x on A and B. So when x becomes the same as y, you get 0. When x becomes larger than y, we get negatives, right? What numbers do we use to get to the normal model? No, we're not graphing it. We're trying to find the area under the curve. It's not under the stat button. So that's probably a good guess most of the time, though. Not math. Not program. We've never even used a program. It's not apps. Almost ours. It's the distribution menu. It's a normal model, otherwise known as a normal distribution. So you use the distribution menu. Okay, so let's think about what those meant again. PDF we never use, ever, because it makes a graph for you, but that doesn't help us do anything. Normal CDF helped us find an area under the curve if we had boundaries, which we do in this case. And then normal inverse norm is when you had the actual z-score and you wanted to find, or so you had the area but you want to find the z-score. So we're going to use CDF in this case. Okay? And pretty much all these we're going to use CDF. So if you don't know how to find this, by the end of the second semester, you'll know how to find these and nothing else probably. Because we're going to be doing so many things with distributions. We're going to use normal model again. We're going to use all these t stuff and the chi-squared stuff. We're going to use all this stuff in the calculator. We're going to keep doing this menu over and over and over again. Okay? So CDF. Okay, so yeah, our boundaries are negative 99999, right? Negative infinity to 0. Now, back in the day when we did chapter 6, I made you find z-scores. Right? Which I didn't make you do right now. I made you find z-scores and put the mean as 0 and the standard deviation as 1. But right now, what we're doing, it's fine if you just put in information that you do know. So we know the boundaries are from negative infinity to 0, and we know our mean is 1, and our standard deviation is 0.5. You can change all those things, that's fine. This is what I caution you to. We start reviewing for the AP exam, and we start doing things in the second semester. I'm going to make you write out what you would have to do, and then you can still use this in your calculator. It's fine. Okay? So lower should be negative 99999 up to 0. Mean is 1, standard deviation is 0.5. Paste, hit enter. I'm going to get 0.023. That's the area that's shaded in my picture, and that's your probability. So 0.03 or 3%, that's the chance that the small bowl contains more.
Negative 0.47.
Did you type it in wrong? Are you using CDF?
Yeah.
Did you do negative infinity to 0? CDF, negative infinity to 0, mean is 1, standard deviation is 0.5. So the answer to the question I had up here was 0.0. Well, that'll do it. So your probability is 0.023. That's the answer to that question. The probability that the small bowl contains more cereal than the large one, 0.023. Okay? On D, I'm going to erase some stuff. We're not using that model anymore, so I'm erasing it. What are the mean and standard deviation of the total amount of cereal in 2 bowls? So now I'm not finding the difference anymore. I'm combining them, right? So now I'm just doing y plus x. So how do I find the mean? Add them. So that's 2.5 plus 1.5. So that's 4. And then how do I find the standard deviation? If we're just adding y and x, I'm going to add the variances like we've been doing. So it should be the same thing that we had earlier when we subtracted them. Right here. It's 0.3 squared and 0.4 squared. The standard deviation squared, right? The variances. Right? The difference and the sum, the standard deviation should be the same. Right? Yeah. So on part E, if the total follows a normal model, So n with a mean of 4 and a standard deviation of 0.5. What's the probability you poured out more than 4.5 ounces of cereal in the two bowls together? I think this question's easier if we draw the picture. The mean is 4. We've got 4.5, 5, 5.5. And we want to know 4.5 ounces or more, right? So then we're going to use our normal model in our calculator. So normal CDF, I did the wrong one. Our lower bound is 4.5. We're going up to infinity, if you will. Your mean is 4, and your standard deviation is 0.5. So 0.159. That'll do it. So we're using stuff we learned in chapter 6 to kind of figure out this random variable scenario. Okay. On part F, the amount of cereal the manufacturer puts in the boxes is a random variable with a mean of 16.3 and a standard deviation of 0.2. So this is a new variable. This is puts in the boxes, not what's being poured out in the bowl. Find the expected amount of cereal left in the box and the standard deviation. So remember, we poured one large bowl and one small bowl. We're trying to figure out what's left in this box, right? Don't we already have the totals that we already did?
Yeah.
Right? So on part D, we talked about the combination of what's in the bowl, right?
Yeah.
So to figure out what's left for the mean, what am I going to do?
Add,
How would you know
Subtract
if
the
it means so?
Because the original question way up here a long time ago said you open a new box of cereal and pour one large and one small bowl. That's fine.
subtract the mean, right?
Well, you have the amount that you is in the box,
Yeah.
and you want to subtract out the both of what you added together, the total.
Yes.
Yeah, yeah. So you're doing z minus x plus y, right?
Yeah.
So that's 16.3 minus 4. Yeah, sorry. So 12.3 ounces. How do we find the standard deviation?
Square root of 0.2 square.
Right, so standard deviation is going to be the square root. We're going to have to do some of the variances, right? What's the standard deviation of z? 0.2, so we square that for the variance. Do we ever subtract?
No.
So we're going to add the standard deviation squared from where we combined them. And you should get 0.54. I understand it's a little heavy. This is the standard deviation of the combination. Okay. So I know that's a lot of stuff going on. But it's stuff we've seen before. It's a little bit different. So I want you to try on page 385, number 38.